A little blurry. I don't know why it looks blurry. A little blurry. I don't know why it's so blurry. Let's see what I can do. It does look better, doesn't it? I have to keep it smaller to be clearer. Shouldn't be like that. I don't know. Looks blurry. What if I use my phone? One last thing is to try Buenas tardes, Ricardo. Are you in a chat with the other students? Let them know I logged in. I was in a meeting. I was a little late. Oh, there's people here. Okay. So I didn't start. I'm just playing around with the iPad. For whatever reason, the view isn't great. I'm here just working on projection. I'll start in a minute. So what I want to do today is go over pages after 75. I asked you to look at those on your own for examples, and let's go through them now, and then I'll answer your questions. The test is on Wednesday, 4 o'clock, the first test. Yeah, that's not even working, so I guess I'm going to have to do it this way. And we have Wi-Fi as a backup. I don't know, I just find that the view of the iPad blurry, and I don't know why that is. I don't think that should be. What do you think? Does it look blurry to you? It looks blurry to me, but maybe after the live stream it's not going to look blurry. Buenas, Coral. All right, so let's get going. So I wanted to start here. So I asked you to plug this in. So this was the last problem we did in the notes before. Last week I started with Unit 2 so that you could integrate both the interest rate conversions with the time value of money problems, right? Because I promised you I would test you on those. And let's see, do you think it's blurry? Okay, it looks clear. Maybe I'm just being picky. Okay, maybe it's just my viewpoint. All right, so this is the last problem we did in the notes, page 75, and I posted the markup. Unfortunately, I duplicated the markup up till page 55 or so. So I just put up the markup up to 75, but most of you were in the class, so you made your own notes, right? So you have up to here that we discussed, and I asked you to work on the rest on your own. So the next question was regarding simplifications, annuity with growth. This formula only applies when I is not equal to G. So what do we do when I is the same as G? Well, if I equals G, the problem is this will be a 0. And then this will be a 1. And 1 minus 1 makes 0. So if, let me write this clearer. If I equals G, you're going to have 0 divided by 0, which we say is indeterminate and nothing, like no answer, or does not exist. So in other words, we can't use the formula when I is equal to G. But in fact, an answer does exist. You just can't use the formula, all right? So let's see an example where that's the case. So here's an example where you have a growing annuity, or annuity with growth, and I equals G. You're considering a deal where you will receive $100 cash flow for 4 months, starting next month, and each month thereafter the cash flows will grow by 1%. What would you be willing to pay for such a deal if the effective monthly interest rate is 1%? So here the growth rate matches the interest rate. So this is the interest rate. And this is the growth rate. So it is a growing annuity, but here I equals G. So what we can't use the formula. Instead, we see that the timeline looks like this, right? 1 period from now, 4 periods for the duration of the investment, although there's only, and there's 4 payments, right? But there's 3 periods of growth because growth takes 1 period after the initial cash flow to kick in. So you have the initial cash flow, 1 period, growth kicks in, and it goes up to here. All right, so how do we solve this if we can't use the growing annuity formula? I demonstrate in the notes that what we can do is go back to first principles. We can discount every cash flow back to time now and add them, right? Put them together. Put myself in the camera. So discounting the cash flows to time now means the first cash flow has 1 discount period. The next cash flow has 2. There's a growth period here. So you see these are the same. So you can actually cancel this entire thing with one of these. And what do you have left? You have this amount, which is identical to that one. So what's happening? Growth is offsetting the erosion factor or the discount factor associated with the time value of money, right? So that's what's happening. So this amount is discounted 3 periods. There's 2 periods of growth, however. So 2 of these cancel with 2 of these and leave again 1 on the bottom. So in the end, these cash flows are identical all the way down. And the same thing is going to happen for this one because it'll be 100 with 3 periods of growth, discounted 4 periods, and that's also like this. So, you know, some students try to come up with formulas and or memorize how to do each problem. In fact, you can just rely on first principles, make the timeline. Remember, you have to discount for every period. And in the end, the PV0 here is equal to 4 periods duration of the investment, and each one is worth 100 divided by 1.01. And you can figure out the answer from there. Oh, I lost my iPad. Hold on. It's very sensitive. Came and went. It's not good. A connection. All right, let's see if you have any questions. I haven't been looking at the chat. Okay. Maybe it's just my glasses that make things blurry. So that's $396.04. Maybe I have some sort of protection on my glasses. It should make it clearer. Not blurry. All right, any questions? Is that fine? Did you know that already? Did you look at the notes? Can I continue? The last problem in this set of lecture notes is the application of two annuities in a pension problem. Did any of you attempt this, and were you successful in solving this problem? Did you understand it? Let me know. Okay, so then if not, let's do this together. Well, even if so, let's do it together because I'm sure there's some people would appreciate it. So what you have here are two sets of cash flows. The deposits into a fund, a pension fund, that are going to be $3,000 per year for 30 years. All right, so that's an annuity. Those are the payments, that's the duration, and this is the interest rate, 12% per year. Now this 12% number is rather high, but what it's capturing is that historically, over the last 80 or more years, if you take that data on the stock market, investors who invested in a diversified portfolio of stocks in the stock market, on average, over those years, earned about 12% per year. So if you invest and you leave your money there, you invest in that kind of a diversified portfolio that's captured by a mutual fund, or if you do your own investing and you invest in an index that does the same, that tracks a diversified fund's return, so it invests in the same things that a diversified fund would. So you track that or you invest in that, then you're going to get about you would have gotten about 12%, and we presume that that's going to continue. So with that, let's say in this fund, this would be considered risky because in any given year, it's volatile, right? So it can be a great year, it can be a bad year. Some years you have negative returns, and some years you have positive returns, okay? But on average, so we're going to talk about this when we get to the unit 5. Yes, we will be talking about this sort of thing. How do you estimate these returns? How do you estimate average returns? And volatility as standard deviation of returns. So your statistics class will come in handy. If you don't have statistics yet, I will be doing a review of statistics so everybody can benefit from that. So anyway, so that's what the 12% is intended. So anyway, in other words, I'm saying this is kind of realistic, right? This is a realistic consideration. $3,000 into a fund for 30 years. So if you started now, by the time you were 50, at 12%, if you can find a fund that's offering 12%, like a mutual fund on average, and you keep investing in it, then if the first payment is in 1 year, that's an annuity. Sorry, if the first deposit is in 1 year, that's an annuity. Now, at the end of the 30 years, you start withdrawing from the fund, right? So you've built a fund, a pool of money from which you can withdraw and live on. While you're withdrawing, it continues to earn interest. It'll continue to earn 12%, but your balance is lower each year. And you want to figure out how much you can take out each year to be able to withdraw for another 20 years. So this is a very practical problem, and you have all the tools to answer it. So let's find out how big each payment is. So from the very first day, I explained to you that every position on the timeline has dual perspective. It can be considered the future value of a set of cash flows, but it can also be seen as the present value of cash flows to come. So this is precisely the we're going to take the opportunity to use both sides of this. So we're going to talk about the cash flows going in till the future value to develop the fund, and at this point in 30 years, take that as the amount of the fund from which you can withdraw an annuity of 20 payments to find out what that payment size is. So we have 2 annuities. The first one has a present value of $24,165.55. Now you can put this in your calculator. Remember, on the test, I want to see this. I don't want to see the keys that you punch in the calculator, but for your own sake, you can write them down, right? I mean, I don't want to say I don't want to see them. I just won't grade them. You're not going to get credit for telling me the keys to punch. You're going to get credit for writing this formula out. So you have to practice that. So we're going to enter into N30. Into I will be 12%. Into PV, that's what we want. The payments are going to be 3,000, and they're out of my pocket, so I can put a negative in there. And then FV is not of interest to me. I'm interested in PV for this annuity. Remember, we don't use FV. We don't have to use all keys for the annuity case, only for coupon bonds. So now we compute PV and we get that number. All right, so What I really want, though, is not the present value version of this set of cash flows. I want the future value. I want to know at time 30 how much I have in the fund. So I can press, with the same values in my calculator, I can press the FV key to get this other number, 723,998.05. So essentially, so what you have is about $750,000. So $3,000 every year for 30 years at 12% will give you $750,000. The only challenge here is getting that 12% secured, you know, being confident doing it and sticking with it and not taking your money out of the fund and leaving it there and not needing $3,000 in a year. You can set it aside. So, so that's my fund amount. So now in the second part, determining what the payment size should be, I will let that be the present value amount. Now for 20 years at 12%. So we assume that 12% is still accessible to me as my return, my rate of return. So I continue to use the 12%, right? And now I solve for the payment on this annuity. Entering the values now. I'm going to do this in blue. So now it's 20 into N, 12% into interest, and we're going to put PV, this number into PV. Now to get exactly the number that I have, you should store this number here in your calculator, all right? And you're going to store it as a positive. Or actually, well, anyways, you can store it as a positive, you can store it as a negative. I think I stored it as a negative in the example. So you can change it to a negative using that key. And FV, payment is what we want. And we put 0 in FV. We don't want FV. And now ask to compute payment. And what do you get? So these are the steps. And your final answer should be 996, almost $100,000. Almost $100,000 a year, which is good. I mean, I think it's good. We probably also want to have some sort of supplemental fund to protect us from inflation, right? Our purchasing power. Maybe we'll do something like that as well. Inflation is really out of control. Might want more over the years. But $100,000 a year for $3,000 deposited for 30 years. Keep that in mind. The greatest advantage you students have is time right now. And this is example, just one example of how you can take advantage of time. All right, any questions for me? Okay, any comments? Okay, so then I just have some comments here which can help you for more complex problems to realize how to count the number of intervals in a period of time, which you'd need for certain problems if you want to find out growth, the number of periods of growth, or to figure out also the number of payments within a certain period of time. So for that, you're trying to figure out how many marks, right? How many payments, how many large tick marks there are between 2 points in time. And I give some guidance here. So for instance, how many periods of interest or how many periods of growth are there between the end of the 18th period and the end of the 15th? So as long as you're working from end to end or beginning to beginning, these are the rules you will use. My suggestion is just look at your fingers. If you want the periods of interest or the periods of growth, periods or the space in between, that's simple subtraction, right? So if you look at your fingers, there's 1, 2, 3, 4 spaces between. So if I numbered my fingers 1, 2, 3, 4, 5, then I take 5 minus 1 to get the 4 spaces between. But then how do I count the fingers? In other words, what if these are payments? These are the large tick marks, and I number them 1, 2, 3, 4, 5. Those are essentially the two problems I'm solving. See, so 5 minus 1 is 4, so I have to add 1 extra to get the fingers. So that's what I talk about here. In the case of intervals, from 18 to 55, I take 55 minus 18. That gives me the space in between. But if I want to talk about those as pillars or hurdles or marks, then I have to add 1 So the number of payments between the 19th, the beginning of the 19th and the end of the 15th, I'm just trying to shake it up a little bit there. The beginning of the 19th is the same as the end of the 18th, so I can use that. So end of 18th, the end of the 55th, including 18 and 55, you have to add 1. So these are just 2 rules to remember if you're counting payments or counting intervals. And it also holds true if you go from beginning to beginning. So have a look at that, make sure that that's convincing. And then we move into interest rate conversions. Okay, so now you tell me, what do you want me to work on? I left off with interest rate conversions and asked you to work ahead. There's several applications of the interest rate conversions I discussed, including the daily rate, the quarterly rate, the semi-annual rate, and oh, I missed the monthly, yeah. So the daily, monthly, quarterly, semi-annual rates. So I wanted you to practice that. So any question about any of those documents? Any of the documents would you like me to discuss? Review. I also introduced the idea of continuous compounding and I gave you some examples. So I want to talk a little bit about that unless you want me to start somewhere else. Okay. Okay, I'm here. I'm just going to pull up the interest rate conversions document. I'm here. Okay, so this is the document I shared with you on interest rate conversions. And it has the two broader things you're concerned with. You want to be able to convert between stated rates, what are called stated or nominal rates, otherwise known as stated or quoted rates. So these are the ones we deal with. These are the rates, unless you're told otherwise. And I gave you an example on discounting and inflation. No one's asked me to look at those. But in that example, I introduced the idea of real rates, right? So unless I mention real rates, all rates should be assumed to be nominal. So if you're given a rate from a bank, you should take that rate for a mortgage. Let's say you take that rate and you divide by the number of compounding periods in a year. So if it's a mortgage, you pay 12 months in a year, so that's divided by 12. And what you would be getting is the effective monthly rate. So that's how you use this expression. So as an example, the mortgage rate is given to you as 7%. So then to find out what you're really paying monthly, it's the monthly effective rate, the monthly stated rate divided by 12. So that's 7% divided by 12, whatever that is your monthly effective rate. So it would be, so you'd have to store this in your calculator because it's a repeating decimal, 5833. Percent, to be clear. The other sort of thing you wanted to be able to do is if someone gives you effective rate and you want to convert it, like often you'll be given, or you'll talk about the effective annual rate. So this is actually what is paid in interest, not just simple interest as reflected in the stated rate. This is actually what you're paying in interest on the principal and interest on interest that accumulates. So if you want to convert that into a half of a year or a quarter of a year, why would you do that? Why would you convert it? Well, let's say you make a loan to someone and you tell them, look, if you give it back, if you pay me back in a year, then I want you to give me 10%, for instance. So let's say as an example, let's say you tell somebody the effective annual rate is 10%, but they show up early. Say they show up the next day, okay? They show up the next day and they say, well, here's the money. And you say, wait, you owe me interest. But the person says, but you can't charge me 10%. So what would be fair? What would be the equivalent rate in effective terms that you can charge them for only a day? So you can figure it out with this expression, the effective daily rate. You take this expression and this one and you equate them to solve for the one that you should charge them. So 365 days is equal to 1 year. And there's many other reasons why you want to be able to do this conversion as well. If someone reports to you a rate that is as an effective annual rate, and they might do that so you can compare them to other returns that are stated over the year in effective terms. So they give you an effective annual rate and you want to convert it to understand it in months, let's say, because you want to make payments in months. So you need the effective monthly rate. Or if you want to compare it to mortgage rates. Okay, to solve this, then you would take, that didn't work. That's how you would find it. So you're always going to use 1 plus, like the accumulation factor. And why did I put that? Yes, you have to divide it by 365, but not dividing 1 plus EAR. You're going to partition it in the exponents, right? Because interest has an exponential effect. So it goes into the exponents, and then you take off the principal to know the rate. So this is per dollar. Okay, so with that, let's do some examples together. Oh, I wanted to show you the continuous compounded rate. Well, first of all, let's calculate what that would be then. If the effective annual rate was 10%, then you would take 1.1 to the power 1 over 365 minus 1. So how do you put that in your calculator? I have to check the chat. Let me see if anyone has any comments or questions. I haven't checked the chat. No comments or questions. Can you even see that? It's so bright. It's so light. Make it darker. Let me do it again. And then I'll put the steps for the calculator. Okay, this is one more time. So what I'm going to do is solve for the effective daily rate, knowing the effective annual rate. So I'm going to partition it in the exponents and minus 1 to find the rate. So I'm going to take my calculator and enter 1.1 to the power y to the x 365 and invert it. Oops, invert 365 and then say equals and minus 1. So that is the daily rate. And this is in decimals. So it's really, it's 0.00261158 or 0.02611158%. Now, where does continuous compounding come into play? Where does continuous compounding come into play? Does anybody know? So continuous compounding comes into play. See, this is a string of equalities. This is for 1 year, this is for half a year. You have to accumulate 2 periods of the half year rate to make 1 year. You have to accumulate 4 periods of the quarterly rate to make 1 year. You have to accumulate 12 periods of the monthly rate to make 1 year, and 365 days to make 1 year. What if there was a rate that compounded continuously? So this is getting smaller and smaller and smaller. This is a half year. So first a year, half year, 1 quarter, 112, 365. What about instantaneous? Instantaneous compounding. What would that look like? Okay, wait, let me make these. Instantaneous compounding would fit here. What I'm saying is a continuously compounding rate would look like okay, I guess I have to explain that. So when I've talked about continuously compounding rates, I've written them as R0. In this case, the stated daily rate would be written as 1 over 365, right? And we know we have to divide that by 365 to get the effective daily rate. The stated monthly rate from the bank for a mortgage, we would have to divide by 12 to get the effective monthly rate. The stated quarterly rate, if it was given to us, would have to be divided by 4 to get the effective quarterly rate. So I'm using part 1 above to talk about stated rates. The compounded rate, the continuous compounded rate, is a stated rate, and we write it as R0 because you see these are getting smaller and smaller and smaller to reflect the interval of compounding. The compounding interval is every day, and the smallest you can get is every instant. So that would be 0 size interval. Now, can we divide a number by 0? No, that's not what we're going to do here though, right? We're dividing it by the inverse. So what we're going to do is we're going to divide it. So if you look at the pattern, it's 4, 12. So it's going up in the denominator. So what's the inverse of 0? So it's starting to get complicated, right? So in fact, this is a limiting problem. The limit, so stay with me, you'll never have to repeat this, but I want you to understand where this fits. So I'm going to write R, and I'm going to use the subscript N, just like I explained up here. But what's happening to N is approaching 0. Now remember the relationship between the length of the compounding interval called n, and the number of compounding periods, it's the inverse. So I want to divide by 1 over n, just like here, this 1 over 365 is divided by the inverse of 1 over 365, which is 365. And then what I want to do, that would be the equivalent effective rate. Then I'm going to add 1. I'm going to put it to the power of 1 over n, because that's what I did here. I put it to the power of the inverse of this fraction of a year. And I am going to send n to 0. Now this, you must have seen this function before, or this limit before. Let me put this a little higher so you don't get confused. There's enough things to confuse you, right? So this entire thing is actually equal to E. It's actually equal to the exponential function to the power of R0. So you must have learned this about the exponential function at some point. If you didn't, you're learning it now. So I'm going to put it here that this is actually equal to e to r 0. So we call all r0 the continuously compounded rate. And I never mentioned this again, but I just want to tell you how this fits. It follows the same pattern as the other ones, where the interval compounding is the smallest, instantaneous. Now, how do we use that? Well, I'm going to link ER0 back to no, I gotta go further. Let me do that again. I need to go all the way back to EAR, and that's how I use it. E to the R0 is equal to 1 plus EAR. And then because of that, I can take the continuously compounded rate and convert it to an effective annual rate. And I might want to do that because I want to compare the offers, right? If I'm looking at an investment opportunity that's stated as a continuously compounded rate, then I can convert it to an effective annual rate to compare to other investment opportunities. So let's look at the exercises that I gave you before we go. I'll just point them out because you'll need to look at those if you haven't already. Okay, let me pull up those documents. I'm here, I'm just getting the documents. So in this case, I give an effective annual interest rate of 15%, and I ask you to find the continuously compounded rate. So the rule is that ER0 is equal to 1 plus EAR, using the justification that I provided earlier. So this is EPR1 or EAR is 15%, and then you want to find R0. So this is algebra. And once you know the principle, you understand the finance part of it, then it's just algebra. So how do you solve for the exponent here? You have to take the logarithm of both sides, the natural log, which will reduce this here. And then this will become 0, not 0, sorry, 1, because they cancel each other, the natural log and the exponential, or the or e, right? So they cancel, the actions cancel each other, leaving the constant R0 is equal to ln of 1.5, which I find to be 13%. So they're, in the end, 1.15, in the end, they're very close, right? 15% and 13%, almost 14%. They're very close, but they're different. And remember, banks, investment banks, financial institutions, they work in trillions of dollars of balance sheets. So those small differences make a difference for them. So they should make a difference for us too. We should know how they're computing things. And I mentioned that you follow the instructions I provide to give me the same number of decimal places as requested. In fact, your calculator stores more than it shows on the screen. So do not round intermediate calculations. Always store. If you're going to use this number for something else, you're going to need to store that number and then recall it. All right, so that's all the time for today's class. If you have any questions before the test on Wednesday, please contact me. If you want, we can meet virtually. Otherwise, I'm not going to meet in person. However, I need to tell you, and I will send an email about this, I have reserved, I think I mentioned it last class, I reserved a classroom for students in Plaza Universitaria. It's available from 4 to 5:30. For you to be in this class, to watch the class, if you want some quiet, it's reserved for you to be there. So if you're on campus and you're looking for a quiet place, you're welcome to go there. It's reserved for us. So I'll be there on Wednesday if any students want to come there to sit and set up and write their test. The test will be online for an hour and 20 minutes, and you can set things up in that room. Okay, so maybe I'll meet you there, or you'll be writing at home. The exam will open at 4 p.m. and it'll close at 5:20. Any questions for me? So you can use anything you want, all your notes, the videos, you can do whatever you want. You just can't talk to anybody. You have to write this test on your own. And it's going to be multiple choice questions. It's a short period of time, not going to give you too many, so you should write your solutions on a piece of paper before you decide, and I'm going to have you upload your solutions to the platform as well, so I can see those. In case there's a misunderstanding about a question, you can ask me. You can have me look at your solutions, but I'll need a record of them in the Moodle platform. No questions for me? No comments? The test is worth 10% tomorrow. I'm going to double check that, but I'm pretty sure. That it's worth 10%. It's not a lot, but it'll give you good feedback for whether you're on the right track. Okay. All right. So have a good afternoon. Have a good evening. Keep in touch, and I will talk to you and see you on Wednesday if you come to the classroom. Bye for now.